Welcome to Matematika. Today we're going to review about exponential functions. So an exponential function is a mathematical function of the form of f of x equals a times b to the power of x, where a is the constant term and that is the coefficient, b is the base of the exponential function, and that's a positive constant, and x is the exponent, and that is variable, a real number. So we call this as our exponential model. That is f of x is equals to a b to the power of x. We'll get to know this model later on. All right. Now, we often see a graph like this. Okay, the graph goes that way. And this is one of example of a graph of an exponential function. Whether the graph goes up to the right or the graph goes down to the left. It's curved, okay? Curving up, curving down. All right. Now, we can see some examples like we have f of x 4 to the power of x. And you can tell right away that that is an exponential function. Another example, when you can see something like this, e to the power of 1/2 x, or you can have e to the power of x over 2. That is an example of exponential function. You can have either also e to the power of, let's say we have a negative exponent, negative 1/2 x. That is an example of an exponential function. All right, let's get to know more. Exponential function is classified into two types. Okay? One is the exponential growth. Okay? And it's a function, the function is increasing. So the quantity increases slowly and then progresses rapidly. It increases slowly and rapidly it increases. Right? As we can try to imagine like a graph going that way. All right? An exponential growing function has an increasing graph. So this is what I mean by increasing graph. Okay? And it can be used like, where do we see that? A problem in economic growth. We can see that in population growth. Okay, how about expansion? You can see this problem. Compound interest in the bank. Okay, we have exponential growth. We use that. The growth in bacteria in terms of medicine. Growth of bacteria in culture. What else? As population increases, I have here population increases. So it's indicated as increase. We are going to use this formula. All right? f of x equals a times the quantity of 1 plus r to the power of x, where a is the initial value or amount, r is the rate of growth, that is, r should be greater than 0. X is the number of time periods have passed, and f of x is the remaining amount after x time periods. All right, I will be giving you an example problem on exponential growth later on. Let's do the second type, which is the exponential decay. That is, the function is decreasing. That is, the quantity decreases very rapidly at first, then fades gradually. So we see something like this in a graph. Okay, you can see that it decreasing. Our function is decreasing and fades gradually. When it reaches to the x line and then it touches the line, it gradually fades. So an exponential decay function has a decaying graph. So you say decaying graph. Actually, this is the term for decreasing graph. All right. In a problem like this, we use a decaying graph. So the exponential function can be, exponential decay can be used to determine like half-life problem. Half-life problem. What else? Mean population decay. That means it's decreasing population. Radioactive decay. Getting the mean lifetime. We usually use the decaying, formula. And that formula is f of x equals a times the quantity of 1 minus r to the power of x. So I want you to look at the difference here of the formula. In growth, we have 1 plus r, 1 plus the rates. While in decay, exponential decay, we have a times 1 minus r, because the a here is less than, or the r is less than 0. So a is for the initial amount or value, r is the rate of decay, that is r is less than 0, and x is the number of time periods have passed, and f of x is the remaining amount after x or time periods. Okay, let's apply this into a problem. When I was a student before, many of my classmates were debating when to use the decay and when to use the growth. I think it doesn't come into our mind at the time that this is what we're supposed to do when it's growth, and this is when it's decay. All right, let's do this in a problem. The world population in 2000 was approximately 6.08 billion. The annual rates of increase. So you see this term, rate of increase, is about 1.26%. All right. A, find the growth factor for the world population. Okay. If we try to look at this, we go straight to the formula that we can use. That is this is a growth. F of x equals a 1 plus r to the power of x, since this is the growth. Now, the first thing you do when you have a percentage or percent given, you change the 1.26 into a decimal. So we move 2 places to the left, so that will become a 0.0126. So that it will be in our advantage when we try to solve this kind of problem. Where can we get the growth factor? Okay, the growth factor is here. Okay, in the formula. So it's 1. All right, 1 plus r, our rate. This is our rate. So 1 plus 0.0126. That would be equals to 1.0126. And that is the rate growth factor. Okay. Let's move on to the second question. Suppose the rate increase continues to be 1.26%. Write a function model the world population. Okay, function model. So we can get it from here. I will change the f of x into a y. It's a function model. Then I would say a 1 plus r to the power of x. So, we'll substitute the value. Y is equals, our a is the coefficient, and that is the initial value, initial amount, 6.08 billion. All right, that's the initial amount. Now, we'll substitute that 6.08 times what is our 1 plus r. We have it already here. That is 1.0126 to the power of x. And our x is the time. T. Okay. This is now the function model. Okay. Now letter C. Let x be the number of years. So as I've said, x equals t, the number of years past the year 2000. So from 2000 to 2010, the time is 10 years, right? From 2000 to 2010, the time difference is 10 years. So substituting to the equation, y equals 6.08 times 1.0126 to the power of 10. So it will be easier for us to compute. So using the calculator, we can compute. We come up with the result of 6.89 billion. So after 10 years, so when it was 2005, the population was, what was that year? 2000. The population was 6.08. After 10 years, the population becomes 6.89 billion. And this is the answer. I hope everything is clear to you at this point. Okay, let's do a second problem here. A computer valued at 6,500. Okay, that's the value of the computer at first. So I might as well write it here. So the initial amount or the value is 6,500. That's A. And then what else is given? The rate is given at 14.3%, or we can change that into decimal by moving 2 places to the left. That would be a 0.143. Okay? I'm going to write this again to make it clear. 0.143. So we have two values that are given here. Now, of course, the word depreciates will tell us what formula we're going to use, right? Depreciates, decay, exponential decay. So that would be f of x equals a times the quantity of 1 minus r to the power of x. Remember the formula I've given above when it's decay and when it's growth. And decay is 1 minus, while growth is 1 plus. All right? So write a function that models. I will change the f of x to y. So a is 6,500. Then what is 1 minus our rate is 0.143 to the power of, we can make the x here as the time to the power of t. All right, simplify. 6,500. 1 minus 0.143, that is 0.857. to the power of t. This is the model. All right. Then you're asked to find the value. What is our time? Do we have the time here? Find the value. Oh, find the value of the computer after 3 years. So our t is 3. All right, it's there in the problem. So find the value. What would be the value? It will, of course, since it's decay, it will depreciate. And the problem says depreciates. All right? So if you come up with an answer greater than 6,500, then your solution or your answer is wrong. It should be less than 6,500 because it depreciates. All right? So let's have 6,500 times 0.857 to the power of 3. You can multiply 0.857 to the third power, then multiply 6,500. Or you can do it in the calculator directly. And you come up with an answer of 4,000. So this is in terms of dollar. 4,091.25. So after 3 years, the 6,500 computer depreciates, and it is in the value of 4091.25. This is the answer. I hope this helps a lot in your review about exponential function, exponential growth, and exponential decay. Okay, if I can do it, so can you. All right, I hope you click a like, and subscribe. Thank you. See you in my next video.